Need to make myself heard. Okay, hello and good afternoon. Welcome to the 5th lecture already of Module 2, Circuits of EECS 16. Okay, so, hey, you won't believe this, what happened to me. Yesterday, I spent all day from 7 o'clock in the morning to 10 o'clock at night. I spent in the lab and I measured 4 different circuits. And just when I finally was done and was getting out, I had plotted all my results, IV characteristics, I plotted them on a sheet of paper, they fell down, and I don't know anymore which plot belongs to which circuit. But hopefully you can help me. So we're not going to talk about all 4 different circuits. The one that I'm most concerned with is this one. It's got lots of different sources, it has lots of resistors, and I plotted the IV characteristic. And let's just discuss on how I did this. Okay, so what I did was I connected here a test source. Let's call it I test. And then I measured the voltage V test that I got. So I dialed different currents on my supply. I had a current supply. You have one in the lab too. And then I measured the voltage with the voltmeter, and you know that too. Okay. So then what did I get? Let me plot this here on this other sheet of paper. So here we have I test. So that's what I put in. And then here we have V test. That's what I measured. Okay, and so I got 4 different, or at least 3 different results. So let me plot those. So one of them looked like this. Let's call this A. The other one I did looked like this. Let's call this one B. And there was also a third one that I measured, and let's call that one C. We'll talk about the 4th one in just a moment. But for the time being, let's just figure out which IV characteristic, A, B, or C, belongs to this circuit here. So I don't have to redo all my work. Any suggestions? Well, who is for version A? That IV characteristic A is what I got when I measured this circuit. Nobody. Well, that's good. But why? Why is it not possibly the case that I got IV characteristic A when measuring this circuit here? Well, let me ask a little bit differently. This characteristic A has a kink here. Somehow, so this is horizontal, and then suddenly it sort of starts bending over, and it sort of gets almost vertical. What element produces such a thing? Yeah, what? A battery. A battery would produce a characteristic that probably would be fairly similar to this, right? As we pull more and more current, then at some point the battery just says, hey, cut it out. That's too much for me. I cannot hold my voltage. What is a battery? How would you model a battery with one of the circuit's elements that we know? Yeah? With the voltage source. But does a voltage source have this characteristic A? No, right? A voltage source, it would just keep going on like this. And I guess if we were completely precise, then we would say an ideal voltage source. And in our circuits, these elements, these circles with pluses and minuses, those are ideal voltage sources. So if I had ideal voltage sources in my circuit, I measured it, I could not possibly have gotten the characteristic A. Okay? What about characteristic B? Is that a possibility? Anybody is for B? Yes, 1. Okay, great. I mean, actually 2. So, and now, if I ask again, who is for B? The number increases substantially, okay? It's still many of you you have no opinion. Hey, you got to vote. Okay, so can you give a reason why you think B is actually the right choice?
It seems as if that the line should be linear because it's pretty much consisting of just
Right.
a couple voltage sources. And also, I looked at C and it just seems a little bit funny. Like, why would, as you increase current, voltage becomes negative, or if current is negative, voltage, I don't know. I've never seen it before, so maybe that's not,
Okay, we'll talk about C in just a moment. But let's stick with B. Yes, so the most likely choice is B. C is also a candidate. But why is it B? Well, we've said before that when you do node voltage analysis, you describe a circuit with just the matrix A that we figure out by going through this node voltage analysis procedure. A vector V, those are the node voltages, and that is equal to another vector B, and that vector B is the value of the sources. Like here we have 2 voltage sources and the current source, so the spec values, the 500 milliamp current of that current source, the 3 volt voltage of the voltage source, and so on, they would show up in this B part. And that also, you get that out of the node voltage analysis. And we already last time we said, let's just multiply both sides of this equation with A inverse. And again, let's assume that there is an A inverse. Well, then we get A inverse times A is going to be the identity matrix, so we don't need to write that there. It doesn't do anything, multiplying with 1. And here is A minus 1 times B vector. Okay? So basically what this equation tells us, that all these voltages that we measure, so including V-test here, they are going to be simply linear combinations, appropriately weighted, of the values of our sources. Again, the voltage and current sources in that B vector. And we multiply their contributions with different values that depend on the resistors and other possible elements that we have on our circuit, the topology and so on, right? Voltage divider would be a simple case or so. And consequently, there is nothing in here that says, hey, you suddenly get discontinuity and a kink, like in this A curve or so. It tells us that we get some linear characteristic like that, like B. If there were no sources present, only resistors, what would you expect? Would you expect a similar curve? Which curve would you expect, actually, if there were no sources present in that circuit? A, B, or C? C. C, right? Why would you expect C? Well, because at least one point we should be able to agree on, that if the voltage is zero, the current also has to be zero. A resistor is not somehow a miraculous source. It cannot put out power. So how could a resistor generate? If you have just resistors, even if you have a million resistors, how could a million resistors suddenly produce a voltage if there wasn't a source somehow to help them, right? So if it was just resistors, we would have to get something that looks like C. Now, your point. You said, this is funny. Why does it look like this? Well, the reason it looks like this is because of the way I've defined the directions of I test and V test. They look just fine. It looks like passive sign convention, right? But if I were to say, here I have voltage V test, and here I have current. Well, for this, so if let's say, let me maybe draw this again. If we make this whole blue thing, we make this a black box, and we call this a circuit element. So it's a circuit element. So now, how would we define voltages and currents for this circuit element if we use passive sign convention? Well, we would have here V element, and here we would say the current needs to go from plus to minus, so this would be I element. But look at the other part of the circuit. Here we had, these are connected. Here we have our test source here, like this, and this is I test. And then this is V test. Right? And so here is also I test. So this here is passive sign convention. And this also is passive sign convention. But notice, if we mix I test and V element, then we suddenly get something that's no longer active sign convention. Right? I test goes actually this direction. Right? So I test, or I element, is equal to minus I test. I mean, this is simple if you want geometry or so. I mean, you define the voltage from top to bottom, right? And then the current also flows from top to bottom. Well, but then this current needs to be, for being also passive sign convention, needs to go the other direction. So be careful about that, right? If you define multiple currents or so, then you may end up with non-passive sign convention. It's called active sign convention for if you combine them in different ways. So the way we fix this is simply to realize that these currents, they're not the same, they're closely related. One of them is the negative of the other one. But if we, for example, wanted to figure out what's the power dissipated by the blue box or by the test source, well, then we would have to make sure that we are in passive sign convention. Otherwise, we got the wrong sign. Okay? Does this make sense? So otherwise, look at that a little bit more. So that's important not to get confused. So incidentally, so that's kind of a bonus question. I could also have, if I had measured something like this in that particular circuit, so D. You think that's possible? Well, I'll tell you. You can create this, but you need negative resistors. With sign conventions that we've used here, to create this, you would need negative resistors. Okay? Of course, if we define the signs differently, then suddenly the curve look different. Okay? So just be very, very careful about signs. There is nothing wrong here. This is passive sign convention. This is passive sign convention. I test and V test, passive sign convention. I element and V element, passive sign convention, everything fine. But if you suddenly mix V test and I element, well, it's not passive sign convention. You got to stay consistent, right? Okay. And you can see that easily by looking at the direction of the currents, just like we have done there. Okay. So, thanks for helping. So I don't need to do another night shift. So now there is something kind of interesting. We had this circuit here that is kind of complicated, right? It's kind of nasty. And we said, this circuit can be described just by a straight line like this, in particular line B of all of our choices. So, would there be other circuits that also could generate this line B, that also would have an IV characteristic that's described by B? Can you think of another one? Or at least do you think there are other circuits that produce also a characteristic that looks like B? Yes, somebody at least seems to agree with me. Okay, so there are other ones. So we could ask ourselves the question, if we wanted to build a circuit that implements this IV characteristic B, what would be the absolutely simplest circuit that we could design that has this characteristic? Any guesses for that? Yes, back there. Would a voltage divider do that? You sort of, but yes. A voltage source and just one resistor. I like that. Let's try this. So, let's have a voltage source. Let's start with a voltage source. With the value VTH, we'll talk about just in a moment why it's called VTH. Of course, you can give it another name if you prefer. Okay, so we have this voltage source. Now we need a resistor. Where does the resistor go? Yeah, well, anybody else suggest, if we want to generate characteristic B, where would you put the resistor? Well, why don't you discuss this with your neighbor? There seem to be, we have just one resistor. There are possibilities. Figure out how many possibilities there are, and then if you can sort of a little bit more, which of these possibilities is the one that we should choose? Okay, so I guess you're very lethargic today. Why don't you? If you don't know the answer, maybe your neighbor does, or wake him up, or her up, and what do you think? How many options how it can connect that resistor? No, you! One? I can think of two. Okay, so let's see. So first of all, how many ways can I connect that resistor with respect to this voltage source VTH? How many options? Two. Okay, two options. And what are these options? Can somebody describe me one of them? Maybe from that segment. Somehow must be something wrong with the air over there. Kind of puts you asleep. How could we connect? Yes. In series. Okay, so option A is series. So we have the voltage source, VTH, and we put the resistor in series like this. So that's called series. And then there is an option B. Apparently, if there are two possibilities, what would the option B be? Somebody else? In parallel. So let me draw this also, VTH. And we put the resistor like this. So this is parallel. Okay, so two options. Now, remember again, we want to synthesize characteristic B over there in that plot, and which of these circuits can achieve can help us get characteristic B? The series or the parallel connection? The series. Okay, I agree with that. If current starts flowing, again, if we were to put our test source here, I test and we test, and they need to be connected, of course. Well, as I test starts flowing here, we are going to get a voltage drop across this resistor, right? So initially, no current flowing. We have a voltage just VTH. As current starts flowing, the voltage is going to drop. Kind of makes sense, right? There is going to be a voltage that initially, when the current is zero, is also zero. But then Ohm's law tells us, as current starts flowing through our resistor, the voltage across that resistor increases, just like at least I plotted it right. So we start with the high voltage over here, VTH. But then voltage drops, it decreases. The voltage here is higher than over here. Consequently, the voltage over there needs to decrease. As the current I test, if I define it like this. As that current increases, the voltage V test here is going to decrease because we're going to lose voltage across that resistor. Okay? What about what happens over here as I start pulling current more and more? Well, initially, if no current is flowing, what's the voltage here? What's the voltage here? Well, it's simply VTH, right? Simply VTH, because we have that resistor, there are no current flowing. As we start pulling more and more and more current, what's going to happen to that voltage? Yeah, before you... I'm going to start picking on people who... Yeah, what do you think? What's going to happen to the voltage? Okay, somebody else. Somebody can help? It's going to happen to the voltage if a lot of current starts flowing there. Yes? You raise your hand. Anybody has? Yes. The voltage won't change. The voltage here won't change. Why does the voltage here not change? Well, because of the voltage source. The voltage source says that the voltage between this point and 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 this point is VTH because they're connected with wires. It doesn't matter what current is flowing. You can draw as much current as I want. I'm a voltage source. I'm ideal. And the voltage is VTH. Okay? So this circuit here, basically, this resistor R does nothing, contribute kind of nothing to the IV characteristics of the circuit. Of course, there is going to be current running through that resistor. How much current flows through this resistor? Yeah, VTH over R, right? And what happens with the energy or with the power delivered to that resistor? It becomes probably heat if it's a normal resistor, if it's a light bulb, and maybe some of it becomes photons. But this thing is kind of just a heater. But if you were interested in node voltages and so on, that resistor does nothing. It's kind of good to know that and realize that, because sometimes you get a circuit where there are lots of resistors and some of them just plain don't matter, like this one here. And if you just want to calculate the node voltages, well, the first thing you do is not start with node voltage analysis. You look for resistors like that and you eliminate the ones that don't really affect the node voltages in the first place. Okay, so it was a little bit a long, winded introduction to what we really want. We want a circuit that implements this characteristic B, and apparently we need a resistor in series with a voltage source, and the resistor we call RTH. Okay? So, and this circuit is important, and it's so important that it has a name, and the name of the circuit is Thevenin equivalent. Don't forget the accent on the E. Okay. So Thevenin equivalent. Thevenin, it would be the right way to say it, but I guess here you say whatever. Fair enough. Okay, so and the characteristic of this is exactly the line B we had before. So here we have V Thevenin, and here we have I. Well, I test. Let's stick with test. Okay, and if there is no current flowing here, if no current is flowing here, or I test here, and then what we measure is the open circuit voltage. Why do we call this open circuit voltage? Well, no current flowing, that means that I'm not presenting anything, any circuit here. I'm just leaving my Thevenin equivalent open circuited, right? I just present it with an open circuit, so the current is 0, and I can measure a voltage here, and let's call this the open circuit voltage. Okay? So this open circuit voltage is how much? Well, if the current is 0, what's the voltage across our resistor? 0, right? And if the voltage across our resistor is 0, then what is the voltage on the left side of the resistor and on the right side of the resistor? It's going to be the same, right? It's going to be the same. So if over here we have VTH, we're going to have VTH also over there. For I at I equals 0. Okay? So we're going to get one point here, and let's call this V open circuit. Okay? And then we can do another test. We can do a short circuit test. So in that case, we put a short circuit here, and then current now suddenly will be flowing, and we call this the short circuit current, ISC. And what would that be? Well, what's the voltage on the left side of our resistor? Well, it's still VTH. Why is it still VTH? Well, because we have an ideal voltage source, and the ideal voltage source says, and the voltage there is VTH, and I don't care what the current is. It's going to be VTH. But what's now the voltage on the other side, on the right side of our resistor? Yeah, 0, there is a short circuit there. So what's the voltage across our resistor? Well, it is going to be VTH, and consequently the current that is flowing, Ohm's law, is going to be VTH divided by RTH. So we call this current here I short circuit, and that is going to be VTH over RTH. And now, because we know that the characteristic of this circuit here is going to be a straight line, the IV characteristic, we're basically done. We have 2 points, and we know it's a straight line. We can draw the characteristic. Let's do that. Okay. So that's the characteristic of the 7-inch source. What's so funny about it? Okay. So that's the characteristic of the 7-inch source. Of course, we could also have in the lab gone and measured with, let's say, this value of I test, and then we would have gotten this value of V test, and we could have picked yet another one, and gotten these 2 start points. And if we get the 2 start points, we also now know where the line ought to be, right? It really doesn't matter. There is nothing too special about VOC, open circuit voltage, and short circuit current. Nothing too special. We could have picked any values. Yes? Why do we know that V test is going to be 0? Well, anybody can help. So maybe I didn't say that clearly enough. If we put the short circuit, if short circuit means really that we put the short circuit across our 7-inch source. A short circuit's a wire, right? So we have a wire here, between here and here. What's the voltage across that wire? 0, right? The voltage is 0. The voltage here is 0. The voltage across the green wire is 0. The voltage up here has to be 0 too. All right. Okay. Thank you for the question. Good question. Any other questions? Okay. All right. So there is nothing too special about VOC and ISC except for one thing. One thing. Imagine if you had to do this calculation, the calculations with having a voltage source here that was not 0, for example, or a current source, the value was not 0. Would have been a little bit more work, right? Yeah, you could have done it, but it would have been a little bit more work. So the only reason why we like to figure out what this characteristic is using short circuit current and open circuit voltage is that it saves us some work calculating. That's all there is. But if you like to do more complicated calculations, pick the red points. Works too. Okay? So let's do another example. Let's do a second example. Well, or actually the first example if you want. So we have now a new circuit, I1, and so it's a current source. It's loaded with a resistor R1, and then there is another resistor R2, and we want to figure out what is the IV characteristic of this thing, and we also want then to figure out if we wanted to implement this thing with the simplest thing that we know how to implement that IV characteristic, that would be a 7-in equivalent, what would be the element values that we would have to choose. So that's our task. So the first task is we want to figure out the IV characteristic. So what are we going to do? Well, we just went through it. We figured out the IV characteristic of this monster here. Now we have something a little bit different that looks like this. But what were the steps that we did? First step. Yes. First thing, we find out what is the open circuit voltage. Perfect. Let's do that. So what's the open circuit voltage? Well, open circuit voltage means that there is nothing connected over here. So it's just the voltage that we get here. So now you could do node voltage analysis to do that, and I'll say this later again. And that's a really good idea. Okay? Do that. In class, I'm not going to do it because it takes a little bit of time, and also because we can get a little bit of circuit insight. But if you're a bit confused, just use node voltage analysis, because it always works. A computer can do it. And hey, you're much smarter than a computer. Maybe the computer's a little bit faster, but you're much smarter. Okay? Well, if this is open circuited, this current I1 here, of course, is going to flow out of the current source, right? Where is it going to go when it finds these two resistors? Is it going to flow into R1, or is it going to flow into R2? Into R1. Why? Well, because if it flows into R1, it hits a dead end over there where the plus sign is. There is nothing connected there because it's an open circuit. It cannot go any further. So it doesn't like that. It needs to flow the other direction. So I1 is going to flow here, and it's going to produce a voltage drop across the resistor. Ohm's law, this is going to be VOC is going to be equal to R1 times I1. Okay. So that's A. That's step A, the open circuit voltage. Now we're gonna present a short circuit, right? That's step B. We're gonna present a short circuit, and we want to know now the current that's flowing in our short circuit. Okay, so that's ISC. We're gonna have to figure out that one. Oh, that looks complicated. And just to make sure that everybody wakes up, I'll let you do this calculation. We'll have 2 minutes or so, and then we will do it together. Okay? So, you're allowed to talk to your neighbor, get help, and figure it out. You need to do real calculations, so get your backpack open, get your pen out. It's not gonna, you can't do this in your head. I don't think so. Otherwise, you don't need to sit here. You're wasting your time. Ooh. What do you think it is? I'm sure you have paper in your pack. Yeah, but you know, experience helps. That's the only way we can get. I analyzed thousands, perhaps millions of these circuits before I could analyze one in front of 100 or 200 people looking at me and a TV camera. Okay, has somebody the answer? What is ISC? Yes, back there. Okay, let me, so ISC is equal to I1 divide by R1. Multiply by R1 and divide by You're a genius. What? Oh, divide by 2. Okay, genius minus. No, it's great, but okay. But this is good. This is good. So now you laugh. You know how to do it too, right? Or do you think we should do it together? Who is for doing it together? Oh, for once I got a response. Hey, I worked for this one. Okay, thank you. Thank you very much. So you gave us the result. Now we have to produce the same result, us too. So the first thing, if we have this circuit here, it's in 2 colors, but basically the green stuff could as well be blue also. Do you notice something about resistors R1 and R2? They're in parallel, right? So let's redraw the circuit a little bit. And again, that's something, again, I said before, that I analyzed millions or thousands at least of circuits, and it really takes practice. I mean, there is nothing to it, so it takes practice, like everything. Try to play the piano, takes practice. I promise. I'm still trying that one. Okay, so the circuit really is like this, R1 and R2, and the current that we want to know is the current through resistor R2, and we call it ISC. Okay? Do we agree with that one? All right. So now, how would we calculate this current ISC? Well, we could calculate this current using Ohm's law if only we knew the voltage up here. Let's call it V1. Okay? If we knew that voltage, well then it would be Ohm free, it would be just Ohm's law. V1 divided by R2, that would be equal to ISC, right? Okay, so how are we going to get this voltage? Well, we know this current here. How much is this current? I1. But where is this current going to go? Well, it sees 2 possibilities. It sees a resistor R1 and it sees a resistor R2. And which one do you think it's going to take? A little of each, right? It goes, well, if one is bigger, a little bit less current there, but basically the current's going to split. ISC is not equal to I1, right? So the easiest way one way to calculate this is that first we replace R1 and R2 with just a single resistor. And what would be the value of that single resistor? Anybody knows what this resistor R3, the value of this resistor is, so that the circuit is exactly the same as before? Oh. Okay, so that's a parallel combination, R1 parallel R2, and we've derived the equation that's R1 R2 over R1 plus R2. Okay. Now, of course, we know what this voltage is, V1. Okay? Well, this voltage V1 is simply going to be equal, that current I1 is going to flow through resistor R1, so that voltage V1 is going to be equal to I1 times R3. Okay? But now we want to know what is ISC. ISC is equal to the voltage V1, this one here, divided by R2. V1 divided by R2. And so if we pull all of this together, what we get is I1 times R3. Well, that R3, that's here. And we need to divide this by R2. So this R2 business here, this guy just drops away. So this is going to be R1 over R1 plus R2. As the genius told us. Right? So, we got it too. Okay, so now again, how do you calculate such a thing? Well, I've showed you one way. Okay? And I would call this sort of the insightful way. This is not, a computer isn't going to do it that way. A computer isn't going to think carefully about the circuit. Oh, what's really going on? And so the computer is dumb. It doesn't have any clue of what's going on. So it's going to use node voltage analysis. It's going to just plug and churn. In the homework, or more importantly, even on the exam, if you just have a little doubt and you don't see a clever way like here to do the calculation, what are you going to do? You're going to use node voltage analysis. You do that. Some of you have to see this once and then never node voltage analysis again because I'm not a computer. It's too. I don't want to waste my time, right? But some of us, it takes a little bit longer to get comfortable with circuits. This is totally normal. So in that case, there is no problem. Just use node voltage analysis and do it often. Why? Because then you get very good at it. And even though it's a kind of a longish procedure, you can do it fast. I'll tell you, when I was a incoming PhD student at Stanford, one exam, I aced it. I did, as a graduate student, I did node voltage analysis. I aced the exam. After 15 minutes, I walked out because it was easy. I didn't have to use my brain. Just chuck through it. Okay. I handed it in, and the professor looked at it concerned, and so I said, this is not right. Well, it turns out that he had used insightful calculations, but he did it wrong. You know, we all make mistakes. I was right. Okay, so look, just use node voltage analysis. On the exam in particular, you're not under time pressure. A little, sure, you get a, but just go, unless you're really good at it, you see it right away, then of course, use something like this. Fair enough. But otherwise, just use node voltage analysis. If you just start with node voltage analysis and go through it, I guarantee you can ace the exam and you're faster than some others. And you don't make mistakes. You actually get the correct result. So it's nice to do this, but don't stress yourselves. You don't have to do this. Okay. So back to what we have. We've calculated now. This circuit here, we got VOC, that is equal to V7 in, and ISC. We calculated these two. VOC was R1, I1, and ISC was equal to I1 times R1 over R1 plus R2. So there is one thing also that I wanted to quickly point out. Again, sort of interesting. That's sort of the tricks and the sort of the bag of knowledge, the experience that we carry around with circuits. So for some of you, this will make sense today. For some of you, this will make sense in a week or two, and for some of you, it will make sense in 16B. Hey, great! We've seen voltage dividers, right? Voltage divider, two resistors in series. Now here, this could be called a current divider. The current I1 is going to be divided by R1 and R2. And how is it going to be divided? Well, according to this expression. In particular, the current ISC, that's the current that flows through resistor R2. That is going to be equal, it's a little bit like the voltage divider equation, right? Except that in the voltage divider equation, the resistor that is upstairs in the denominator is going to be equal to the resistor that we want to know the voltage across. In the current divider, the resistor that is in the denominator is going to be the resistor that we don't want to know the current through. So we want to know the resistors through R2, then resistor R1 happens to be in the denominator of this current divider equation. Okay? So again, this is something, do you need to know that? No! You can use node voltage analysis and just calculate it. Easy peasy. But if you do know it at some point, when you're in grad school, maybe you can go even faster. You can turn in your exam after 15 minutes and not 20. All right. So, there is something interesting, right? Incidentally, we have, if we were to compare this now to our 7-in circuit over here, right? The one that we had here, 7-in circuit, we get exactly the same IV characteristic, and V7-in is equal to R1 times I1, and R7-in is going to be equal to V7-in over I short circuit. V open circuit over I short circuit. V open circuit over I short circuit. So it's going to be equal to R1 I1 divided by I1 times R1 over R1 plus R2. Well, this looks complicated, but fortunately almost everything drops out, and this is actually equal to R1 plus R2. Okay, so if we wanted to synthesize this source, we could actually use a 7-in equivalent consisting of a voltage source that would have this value, R1 times I1, and we will use a 7-in resistance that has this value, R1 plus R2. There's something a bit remarkable about it. Up to now, when we wanted a voltage source, well, we grabbed the voltage source. When we wanted a current source, we needed to get a current source. But this example here seems to say that if I have a circuit that, in this particular case, uses a current source, I can implement this circuit just as well using a voltage source. Kind of neat, right? So, so by extension, we kind of would think that we should be able also to implement, therefore, a voltage source with a current source. Yes. Are there any limitations where you cannot just take a current source to make a voltage source? Yes, there is a limitation, and the limitation is it doesn't work when it's ideal. In other words, when the value of this resistor here, RTH, is 0, if RTH is 0, then you have a singularity, it doesn't work. Okay. So from a mathematical point of view, this simply doesn't work. It's not universal, right? From a practical point of view, it doesn't matter. Why not? Because ideal voltage sources don't exist. You can work as hard as you want. The actual voltage source is going to have an output resistance, RTH, that's not going to be exactly 0, a little bit more. At the minimum, you have a wire there, and that wire has a little bit of resistance, right? So, in practice, you're absolutely right. There are limitations. From a mathematical point of view, I have no argument with that. But from a practical point of view, it's sort of secondary. Okay. But you're right. We have to be a little bit careful. Okay. So let's try to make a very simple source that has this IV characteristic here. So that's I and V, where we are not using a voltage source, but now we are using a current source. So we start with the current source. The value of this current source, I call it IN. Okay? And then the current, of course, that flows out of our current source is going to be equal to IN. And So, and then on the other side, we're going to put again this test business here. I test and we test. Okay? So, now we're also going to need a resistor, right? We're going to need a resistor, and we're going to put the resistor in series with IN, or we're going to put it in parallel with IN. Well, if we put the resistor in series with IN, will it affect the current in any way? No. So it's just like putting a resistor in parallel with a voltage source. It sort of produces heat, all right, but other than that, it doesn't really do anything to our circuit. So here we want to put a resistor in parallel. So this is Rn, okay? So now we have made another, and you can calculate what VOC is. VOC, well, we have nothing over there. There's no current flowing here. So VOC is going to be IN times Rn, and I short circuit, well, that is going to be, there is a short circuit over here now. The current IN arrives at this junction. It can go either through the resistor Rn, or it could also go through the short circuit. What's easier for the current? Short circuit, no resistance. Hey, I always take that one. Okay, so therefore the current all is going to flow through the short circuit. So IC equal to IN. So now apparently there are two ways we can model sources. One of them is with the Thevenin equivalent, this one here, voltage source, and a resistor in series, and the other one is called the Norton equivalent. Okay, so let's do a little summary here. We have apparently two possibilities. We have Thevenin and Norton, and one. Sometimes you prefer one, and sometimes the other. So it's good to be able to switch between the two. Again, these are models. Your actual circuit may be much more complicated, but the model is very helpful because it's simple. And we'll see examples in the homework and so on where we can use it to synthesize, design stuff that would be difficult to design otherwise, would be complicated. So here we have I Norton, and we have R Norton. So this is just what we had before. I'm just redrawing this. Okay. And so then for both circuits we can calculate what is V open circuit. Well, for the Thevenin that is just equal to V Thevenin, and V open circuit for the Norton, that's going to be IN times Rn. We've done this all before. Likewise, I short circuit is going to be equal to V Thevenin over R Thevenin, just KVL and Ohm's law. And I short circuit here is going to be equal to IN. Okay? So we now can set these equal. For example, V Thevenin, the open circuit voltage is same. If we want the circuits to behave the same, then V Thevenin is equal to I Norton times R Norton. So if we had a Norton equivalent, well, we could turn it to a Thevenin equivalent, and we have to choose the voltage of the Thevenin equivalent to be IN times Rn. Likewise, we can put these, set the two we can set the currents. Yeah, we can also the Rn is equal to VTH over IN, and that is also equal to RTH. So apparently, the resistors in the Norton and the Thevenin, they're exactly the same. It's just in one case we have a voltage source, in the other case we have a current source, and we can use this little expression here to convert between the two. Simple. Okay? Yes?
Wait, can you explain what you mean when you said the VOC on the left side, the V open circuit on the left side and V open circuit on the right side? Like, how are you making those two equations?
If I want those, so the question is, how do I make these two open circuit voltages equal or so? So what I have is I have two possible circuit implementations that implement an IV characteristic that looks like this one, okay? I want them to be exactly identical. I want them to behave the same, that if I wrap it up in a black box, and afterwards I hand you the black box and I ask you, which one's inside, this one or this one, you have no way to tell because they behave exactly identical. If in that case, they also must have exactly the same value for VOC. And they must have exactly the same value for ISC. Okay? So I can set these two equal. Then, because the circuits are supposed to be equal, the equations that describe them must be equal too. I can convert between the two. Okay, good question. Any other questions? Yes. The question is, how do we know whether it's preferable to use one or the other? Well, really there is no general answer to that. But imagine that if you had a situation where R7 was a really low resistance, right? Then it would be almost like an ideal voltage source. In that case, you probably would be inclined to use the Thevenin equivalent. On the other hand, if R7 turns out to be a very large resistance, 100 megohm or something like that, 100 million ohms, well then probably there would be very little current flowing through this Norton resistance, right? We would use the Norton equivalent. It's almost like an ideal current source. Not quite, there is this 100 million ohm there, but cool. Right? So that's why in practice we use both. And as you gain more and more experience with circuits, build more and more complicated stuff, you'll find more and more situations where actually this current source, like transistors, they really, very often they behave more like current sources than voltage sources. So then you use a Norton equivalent to describe a transistor circuit or so. Okay. Any more questions? Yes. How do you get this equality? Let's see. It's hard to think in front of that many people, hey, you know. So what we do is basically we have these two equations, right? Both of these are equal, and I solve these. So how do I do this? If I VTH over RTH is equal to IN, and VTH is equal to IN times RN. So that means VTH is equal to IN times RTH. Well, if these two VTHs are actually both VTH, meaning equal, and these currents, of course, they're even called the same, they're equal, then these two guys sort of must be equal too. I'm sure there is a better way to do this is Gaussian elimination. But, okay, so we have it, all right? Good. So we've gone some ways on circuits, and the next topic is going to be capacitors. Now, I won't have time to start with capacitors today, so instead, let's make a summary of the kind of circuit analysis techniques that we've learned so far. So these are all sorts of bits and pieces, things that we can use for circuit analysis. What was the first thing we learned about how to do circuit analysis? There were laws that were named after what sounds like a German, has a funny name. Kirchhoff's laws, yes. KVL and KCL. Right? Those are laws that are really very useful. They're very simple, but they're very useful. Then there were other laws, in particular Ohm's law, that also were useful. And when you have these, the Kirchhoff's equations that really explain what's going on with voltages and currents in circuits, and element laws like Ohm's law that explain how elements deal with voltage and current. If you put these two together, you can figure out all the voltages and all the currents in any circuit that you're interested in, okay? So that's the basics if you want. Now, in principle, we could have stopped there and we could have saved ourselves a lot of time, right? 4 or whatever lectures. But the trouble is, it's a little bit tricky sometimes to just use these laws and exactly how do you need to use them. And today we sort of use some examples. So then we introduce node voltage analysis. That's a procedure. On how to do that, and there are of course lots of different procedures on how to use KVL, KCL and Ohm's law in order to determine the currents and voltages in our circuit. The special thing about node voltage analysis is that it's very systematic, no thinking involved, a computer could do it. Okay. So this is, and it's universal. So as I said already before, this is our method of choice. Method of choice. Whatever. Okay? So then the last couple of lectures, we started learning about other ways also how to analyze circuits. Do you remember one thing that was very helpful? Yes. Which one? Okay. Series parallel combinations of resistors. Yeah, okay. So let's put this under a general sort of heading, and that is equivalence. Right, equivalence. We found that certain configuration of lots of resistors, for example, 2 resistors in parallel or 10 resistors in parallel, they behave just the same like just one resistor. Okay? They are equivalent. Why are they equivalent? Because they have the same IV characteristic. Okay? So, equivalence, we've seen that for resistors. Series and parallel. Okay? Have we used equivalence for something else also? Have we seen that very complicated circuits, they have an equivalent that is much simpler? What about this circuit here? This circuit here, it's complicated, right? It's complicated. Is there a simpler equivalent that has the same IV characteristic? Come on, I mean, you slept today? I could sell myself as a sleeping pill. Yes. Okay, yes, that's right. We could use superposition to analyze this circuit, and it's not so bad to analyze. But let's ask ourselves, is there a simpler circuit than this one that is equivalent, that has the same IV characteristic as this one? Remember, what was the IV characteristic of this one? Well, where did I put it? Here. No. Yeah, here. What was the IV characteristic? Was it A, B, C, or D? Was B, right? Now, do you know another circuit that also has this IV characteristic B? Okay, so okay, Thevenin and Norton equivalence. Very helpful because things can get hairy and complicated quickly, but if we know simplifying equivalence, then we still can think about circuits without getting a headache. That's useful. Okay, so then one of your colleagues already suggested superposition. Superposition, there are really two things about superposition that are important. One of them, it's an analysis technique. A circuit with tons of sources, 20 voltage sources and 15 current sources or so, we can analyze much more simply if we sort of do divide and conquer. We pick one source at a time and all the other ones we set to 0 and then we pick the next one until we're through. Okay? It's work. But if we behave like a computer, it's just that, right? We can do it at 2 o'clock in the morning if need be. Okay, so it's for analysis. And the other one is understanding linear superposition. It's very important. It will be more important in subsequent courses or so, where we realize that certain circuits, linear circuits or linear systems, they really behave to different sources. They behave by taking all of these sources and doing linear combinations of these sources. And we found that to be the case by formulating our circuit as a linear system of equations. Okay, so most important thing for now anyways you want to carry away is that you have lots of ways to analyze circuits. If anything is confusing, then you always have one way that always works, that it's just a little bit of work, but there is plenty of time on the midterm exam. I promise you that you always have enough time to use node voltage analysis. The exam is going to be designed very carefully to make sure that that's the case. So you all can ace the midterm too. And then there are other techniques that over time you will get more comfortable with and you can use also. Okay?